So the freezing point and the boiling point of a compound is going to be a physical property that's intrinsic to it. And so we could go look those up for most compounds that we can think of because it's already been measured. And what that temperature is really affected by the intermolecular forces that exist between molecules in a sample of that compound. And so we'll see that the stronger our intermolecular forces are for a compound, the higher the boiling point and the higher the melting point is. And really what's happening there is that we are putting energy into the system, and that energy is being used to separate molecules and break those intermolecular interactions. And when they break them, then the molecule has more freedom to move. So when two molecules are next to each other in the solid state and they're not moving, but they're vibrating, if I put energy into it, I can break that intermolecular attraction between them, and they can start moving in close proximity to other molecules in the liquid state. And then they'll be constantly breaking and reforming and breaking and reforming and breaking and reforming different intermolecular interactions with other molecules in the sample. Once I put more and more and more energy into this, I'm going to give these guys enough kinetic energy to break the interactions completely and separate from one another with enough distance that they're not interacting at all as a gas. And so if it takes a higher temperature to reach the boiling point, it means more energy was required to break those intermolecular interactions. So the stronger the intermolecular forces between molecules, the more energy we have to dump into breaking them to make the phase change from solid to liquid or liquid to gas. Now, the weaker those are, the easier it is to make that transition occur. We don't have to put as much energy into breaking apart the intermolecular forces if they're weak. And so we'll see the temperatures be way lower for the melting point or boiling point for compounds that have weaker intermolecular forces. And so here's an example of that here. We can see we have an ether and an alcohol that have the same number of carbons, same number of hydrogens, and one oxygen each. But one of them has the oxygen bonded to two carbons, and one of them has the oxygen bonded to the hydrogen. So if we were going to list out our intermolecular forces here, these both have London dispersion forces, and I'm going to abbreviate that LD. They probably both have a dipole-dipole moment. This isn't drawn in 3 dimensions, but this oxygen here is bent, and so there's going to be an overall dipole moment in the molecule. So they'll both have that going for them. So they both have dipole-dipole interactions. I'm going to abbreviate that DD. But only the alcohol at the bottom has the hydrogen interaction, and the top one doesn't, because the oxygen is bonded to 2 carbons. And the only hydrogens in the molecule are bonded to carbon. So that's not bonded to an oxygen, nitrogen, or fluorine. So we have stronger intermolecular forces for the alcohol at the bottom and weaker for the ether at the top. And look at their boiling points. So this boiling point is the temperature where our liquid becomes a gas or our gas becomes a liquid. You go either way, right? And so the boiling point for the ether is 35 degrees Celsius. It's way lower than for the alcohol, which is 117 Celsius, which is way higher. So it takes more energy to break those intermolecular forces between the alcohol than it does the ether. And so it has a higher temperature that it has to boil at.